Greetings to everyone. My topic is strain-induced electronic and optical properties of two-dimensional silicon carbide by density functional theory. And these are the outlines of my discussion. And first, let me go to the introduction. Obviously, the silicon carbide is a binary compound of carbon and silicon, and the bulk form of silicon carbide has a wide band gap with high thermal properties and resistance. The monolayer graphene silicon carbide can be extracted from the bulk form, and the monolayer also exhibits large direct band gap, and it shows improved photoluminance, which can be used further in LEDs and solar cells. So you can see the 3D and 2D structure of silicon carbide, and a lot of properties have been calculated by theoretical approach, and we consider the external strain loading regime to calculate and investigate the electronic and optical properties of this material. And experimentally the AFM technique is used most, but which is expensive, so we consider to do DFT calculations to find out desired properties, and we use DFT GGA approach implemented in a course Vista. And for that, first we design and module the structure and relax it to find the equilibrium structure, and we investigate the electronic and optical properties, and then we apply a biaxial strain within the elastic limit by both tensile and compression strain, and we study this optical and electronic properties. And for the optical properties calculation, this code uses first order time dependent perturbation theory, in which it uses self-consistent ground state energy to find the imaginary part of dielectric function epsilon 2, and further it helps to find epsilon 1, and further it uses Kramer-Kronig transformation to find other parameters like reflecting spectra, absorption coefficient, and more. And these are the structural properties that we have obtained after the calculations. Band gap is not so close enough, but other parameters are very close enough to the reference. And these are the electronic properties of the undeformed equilibrium structure, stable structure, optimized structure. And we see the 2.32 direct band gap around the symmetry point K. We see the DOS perspective on alongside the band diagram, and what we have done here is we have applied the optical to calculate optical property. We have applied the light in both parallel and perpendicular directions and investigated all the parameters side by side. So these are the epsilon 1 where we can see the parallel and perpendicular incidence of light, and from this figure we can say that epsilon 1 is positive for a whole range of the photon energy, but in perpendicular we see that the spectra goes down to the negative value, and we say it has a screen plasma frequency, and we can see the static dielectric constant value for parallel and perpendicular. For parallel we see about 2.1, but in perpendicular it is much less than that. And this is the imaginary part of dielectric function. We can see several peaks in perpendicular incidence than the parallel incidence, and we see here the reflectance spectra, where we see the spectra reflectance spectra is in perpendicular directions of incident of light is shifted towards higher energy, that we can say the blue shift, and we can say that beyond the 20 electron volt of incidence of light, this material is totally transparent, and these are the absorption spectra, and these are obtained by the interaction of that incidence of electromagnetic wave with the electrons and holes of the systems. And this is the refractive index of both kind of incidence of light. We see that the refractive index for parallel incidence of light is much than the perpendicular incidence, and more thing can be investigated here. And now we go to the main part. We have this is the figure that explains us the the biaxial strain loading regime, and obviously we provide the strain compressive and tensile strain around minus 16% to plus 16%, and we see energy is very minimum at 0% of strain, that is means in an equilibrium state. And we investigate the bands, and we can see the tuning of band here. And obviously the if you look closer, then we can see when the compression is starting, slowly the band gap is increasing, and not only that, the direct band gap is shifting into indirect band gap, and at around minus 16% we can see a huge indirect band gap semiconductors. And this is the just opposite, that means the biaxial tensile strain. Just opposite happens here, the band gap is reducing, and at around 16% band gap is very minimum, and we can see the conduction band is almost touching the Fermi level. And now here we are explaining the different values of epsilon 2 at different values of applied strain, and we see everything in clearly here. The value is changing within changing the applied strain. We can see in the equilibrium structure spectra by the black lines, and further when we applied the different strain, this data is changing. And the same thing is happening for the tensile strain when the light is parallelly incident, and we see that the spectra is coming at a lower value of energy, and similarly this also changing. We see the normal equilibrium structures, the epsilon 1 value, and when the compressive strain is loaded there, then what we can see is the value of static dielectric constant also decreasing, and when tensile strain is provided, then just opposite happens. Obviously the value of static dielectric constant is increasing, and it goes up to very high values, and we can see the absorption coefficient data here, and that also drastically changing, and we can see the changing pattern here clearly in the figures. And it can be seen also similarly in tensile strain condition, and this also changing drastically, and the reflectance also changes, and in fact the reflectance threshold value is increasing after applying the compressive strain. And obviously we can say although we apply strain, then also after 20 or 22 electron volt, this is again a transparent anyhow, and same thing can be seen here. In this case, the obviously reflectance threshold is a little bit shifting, and refractive index, and we can see here the refractive index for the compressive strain when light is parallel incidence decreasing here when it is compressed, and it is increasing when it is elongated, I mean the tensile strain is provided. And now we will discuss what happens when light incidence perpendicularly, and almost same kind of result can we see, but the fluctuation is a little smaller in this case. And same thing we can see for the tensile strain, and for the compressive strain in perpendicular incidence of light, we can say that the value of static dielectric constant is almost not changing, but we can say that the values are going in more negative values are within the range of 7 to 15, we can say. More negative values it is achieving, that means we can say the more plasma frequency we can see. And same thing is happening here for the tensile strain, but just almost just opposite we can see. And we can see the absorption coefficient here. The values are changing here for the perpendicular incidence of light also. And same thing we can observe here when we apply tensile strain. And these are the spectra, the reflecting spectra. We can say that almost same kind of changing is happening here. And we can see the reflectance is peaks are much increasing when we apply the compressive strain, we can see that. And just opposite happening when we apply the compressive strain, the refractive index is spectra is decreasing. And refractive index is increasing, and we can see that now the refractive index, this is for tensile strain, we can see that the values are increasing up to very high value than the equilibrium structure, and it is going up to 1.7 and more. And it suggests that refractive index can be also can be achieved at high values after by applying the tensile strain and so on. So that was the main result part, and now we are at conclusion, and we say that this monolayer is very stable with good value of cohesive energy. And the electronic band structure displays the direct band gap semiconductor, obviously with high band gap. And with value of threshold energy we see in optical result is much greater in perpendicular direction than in of light than parallel incidence of light. And electronic band gap can be easily altered by the biaxial strain loading, and strain also can load can alter different other optical parameters. And these are the conclusions. And future work, obviously we can check it experimentally, and we can check other properties in experimental way by using other approach, other theoretical approach also maybe. And these are the references, and this is the acknowledged part, and I'm very grateful to supercomputer centers and my supervisors and all people who involved on this. Thank you.